x direction is in some sense a 50-50 mix of spin up and spin down along the z direction. What if we wanted chi minus for the x direction? Then the eigenvalue is going to be minus h bar over 2. So then we would write h bar over 2, 0, 1, 1, 0, a, b is equal to minus h bar over 2, a, b, which is exactly what we had before, except that instead of plus h bar over 2, we've got minus h bar over 2. So if we again cancel out that factor of h bar over 2 on both sides, do the matrix multiplication, we'll get BA is equal to minus AB. What's that telling us? It says B is minus A and A is minus B. Are those two separate things? If B is minus A and A is minus B, there's only one piece of information there, namely they're one opposite. One is minus the other. So this says, oh, let's take it to be B is minus A. So before we normalize, before normalizing, we'll have that the unnormalized version looks like A minus A. And so when we normalize, we're going to again get A is 1 over root 2. So chi minus looks like 1 over root 2, 1 minus 1. Instead of 1, 1, it's 1 minus 1 for the two components. Or minus 1, 1, you know, take the pick. It doesn't matter which one you call plus and which one you call minus. For that matter, we could multiply by e to the I phi for arbitrary phi here. But if we leave it in this form, this says chi minus x is equal to 1 over root 2 chi plus z minus 1 over root 2 times chi minus z. So chi minus in the x direction is also a linear combination, a 50-50 mix of chi plus and chi minus for the z direction, except that instead of both coming in with positive signs, one's positive, the other's negative. So suppose I make a measurement of the x component of the spin of an electron, and I get minus h bar over 2 as a result, and then I measure the z component of its spin. What possible values can I get for the z component of the spin? Jerk, jerk. Plus and minus h bar over 2, right? That's always it, right? Left knee jerks and says plus h bar over 2, right knee jerks and says minus h bar over 2. What are the probabilities of each? 1/2 and 1/2, 50-50, once again. So, the probabilities are just like they would be for chi plus in the x direction, for getting plus h bar over 2 from the x measurement. It kind of makes sense, by the way. Since we're 90 degrees away from the z-axis, it ought to be a 50-50 mix. And in fact, you know, again, I'll let you on your own time get the eigenvectors for sy, and this time they'll have i's involved, but again, it'll be true that it's a 50-50 mix of plus and minus for the z direction, same idea. Now, if I took a direction which was, say, 5 degrees away from the z-axis in the xz plane, well, then what you would find is that the eigenspinners in that direction, for the one for spin up in a direction, and I won't go through the details, although you can get it from one of the problems by plugging in appropriate theta and phi. But suppose that I wanted to measure the spin in some direction which was just a little bit off from the z z-axis, say in the yz plane, just a few degrees away from the z-axis, what you would find is that if I get spin up along n hat, the resulting spinner, written in terms of chi plus z and chi minus z, is mostly chi plus z with a little bit of chi minus z. And if I got spin down along the n hat direction, the resulting spinner is mostly chi minus z with a little bit of chi plus z. But if I go 90 degrees away along the x-axis, the y-axis, or anywhere in the xy plane, then it's a 50-50 mix, because we're as far away as it can be, so to speak, from the z-axis. But if you're close to the z-axis, then the plus gives you mostly chi plus z, and the minus result would give you a spinner which was mostly chi minus z, which kind of makes sense. And again, you know, you can verify that for yourself after you do the homework by just plugging in some values for theta and phi and so forth.
So the x superscript, and y is just the direction along which.
Yeah, the superscript represents the axis along which the angular momentum has a well-defined component. Yes, that's the axis along which it has a well-defined component, plus if it's spin up in that direction, minus if it's spin down in that direction. That's what that represents.
Well, you collect which it makes sense.
Okay, good. I should have drawn the picture earlier then, I guess. Yeah. All right. Okay. Now, we've seen what to do if we've got one electron. What if we had two? Then you just say, God, this is going to be too hard, let's quit. Except you don't, because then you realize, no, I'm sure I'll learn something fascinating as a result of that. And so enthusiastic, with renewed enthusiasm, you plow onwards. Addition of angular momenta. I'll remind you that we did this in Physics 280 in a more hand-wavy sort of way. Addition of angular momenta. And we'll start with the simplest possible case, namely two spin 1/2 particles. Suppose we've got two spin 1/2 particles. Well, here are some possibilities. In the notes that I posted, I'm calling them pluses and minuses, but I'm going to use what's a very common notation and one used in your book as well, which is kind of more pictorial, where you put an up arrow to represent spin up and a down arrow to represent spin down. So in my notes, in my notes there's plus where I'm going to put an upwards pointing arrow and a minus where I'm going to put a downwards pointing arrow. So the state where both electrons have their z component well-defined and equal to plus h bar over 2 will represent as a ket with two upwards pointing arrows in it. And so that represents a situation in which they're both spin up. We could also have the first particle, I'll just say they're electrons, okay, two spin 1/2 particles, let's say they're electrons. First electron is spin up, second electron spin down. I have to be careful because if there are electrons, I can't do this because I have to have an antisymmetric or symmetric spin wave function. So for now, they're just two particles. They're not even identical particles. One is an electron and the other is a proton, let's say, spin 1/2, okay? But you can imagine a state where the first particle, if you can tell the particles apart so that it makes sense to talk about the first particle and the second particle separately. First particle is spin up, second particle is spin down. So first spin up, second spin down. And again, this is all along the z direction. Along some other direction, doesn't look like this. And then you could have that beast down up. So that represents first spin down, second spin up. And then finally you could have down, down, both spin down. Now I want to represent these states with column vectors, just like I did for a single particle. But since there are 4 possibilities now, instead of just 2 like there is for one particle, for one spin 1/2 particle, you just have spin up or spin down, so you need a 2-component column vector. Now I've got 4 possibilities, so I'm going to need a 4-component column vector to represent those situations. And the way we do that is by using what's called the direct product. And this is a bear with me situation, as in the first time you learn how to multiply matrices, you say, why am I doing this? Why do I have these weird rules for taking a set of numbers and another set of numbers and making a third set of numbers out of those? I'm going to do the same thing here. I'm going to give you these rules, and they'll sound arbitrary, and the reason why they're there will become more clear when we show that they do what we want them to do. They represent what we want them to represent physically. So this is going to seem weird and arbitrary, but bear with me. So, to represent these states, we use the direct product. Also called the Kronecker product, and that's what Mathematica calls it, is Kronecker product. That Kronecker got around, as you can see. Generically, if I have 2 particles and I want to represent the situation where one particle is in quantum state alpha and the other particle is in quantum state beta, with a single ket to represent the situation of first particle is in state alpha, second particle is in state beta, symbolically we write ket alpha beta is the direct product, and that's indicated with a circle with a multiplication symbol inside of it, the direct product of ket alpha and ket beta. How do we construct that beast, you say? Well, if I have a spinner, if AB is the spinner for the first particle, in other words, A and B are its components, and CD is the spinner for the second particle, the direct product you obtain by making a bigger column, which looks like this. It's a column of columns, if you will. So the first 2 components are the first component of the first guy multiplied by the second column, and the bottom 2 components are the second column of the first guy times the 2 components of the second column. So in other words, the whole thing, I'm constructing a 4-component column vector out of 2 2-component column vectors according to this rule, which says the components of the direct product, if the 2 vectors involved, if the 2 spinners involved are AB and CD, are AC, AD, BC, BD. But the best way to think of it is probably to remember to take first guy over here and make the top piece be first guy times second guy. Top of first guy times second guy, bottom of first guy times second guy. And that's the words aren't as good as just looking at the picture, of looking at what it looks like over here. And, you know, again, it's like, huh? What are you doing that for? Well, let's watch what happens. So, plus plus, or in my notes, or up up, two spin up guys, is the direct product of first particle is spin up state with second particle is spin up state. And first particle spin up means its spinner is 1, 0. And second particle is spin up means its spinner is also 1, 0. So that'll be, top two components are 1 times the second spinner. Bottom two components are 0 times the second spinner. Or in other words, it's 1, 0, 0, 0. From this we deduce that 1, 0, 0, 0 represents both particles being spin up. So in other words, this first slot must be the up slot, so to speak. So if I've got 1, 0, 0, 0, that represents both particles are spin up because it's got a 1 in the up slot, in the up slot, and a 0 in all the other slots. And the other slots are going to have interpretations in terms of the other possibilities. So if I've got up, down, that's going to be first spinner is 1, 0, taking the direct product with the second spinner is 0, 1, spin down. And so then, I guess I could put it, the intermediate slot would have been, I would have been up, cross, down, up direct product with down. So maybe I should just throw that in there. So up, direct product with down. So now that's 1, 0, direct product with 0, 1. And then that says 1 times the second spinner for the top two components, 0 times the second spinner for the bottom two components. So I get a 4-component vector 0, 1, 0, 0. So in other words, the second slot down is the up-down slot. So if the first particle spin up, the second particle spin down, I represent that with 0, 1, 0, 0. Then there's first particle down, second particle up. So that's direct product of down state with up state. So now I've got 0, 1, direct product with 1, 0. So I compose that by taking the first two slots are 0 times the second spinner. The next two slots, the bottom two slots are 1 times the second spinner. Second spinner's up. 1, 0. So that turns into the 4-component column 0, 0, 1, 0. So slot number 3 is the down-up slot. And then you can probably predict what the bottom slot's going to be. That would be the down-down slot. So down-down is down, direct product with down. So 0, 1, direct product with 0, 1. Top two components are 0 times column 0, 1. Bottom two components 0, 0, 1. So this guy is the down, down slot. Okay, any questions? So, if we get fancy, if we call the space of states for particle 1 V sub 1, so vector space of states for particle 1, and for particle 2, maybe I should put for particle 1, I don't like the punctuation. For particles not 1V, for particle, call V1 the space of states for particle 1, might have been a better way to say it. And for particle 2, we'll call its space of states V2. We call the space of states for the two-particle system V1 direct product with V2, the direct product space and now here's a tongue twister, head swimmer, whatever. Well, let's see. The direct products of bases for V1 and V2 is a basis for V1 direct product with V2. And that's what we did over here. In other words, the basis for the states for particle 1 was spin up and spin down, 1, 0, 0, 1. Certainly, any two-component column vector can be written as a sum of 1, 0, and 0, 1 with appropriate coefficients, right? Because A over B as a column is A times 1, 0 plus B times 0, 1. So obviously, any state can be written as a sum of spin up and spin down. Similarly for the second particle. Now, we created four component column vectors, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Do those constitute a basis for everything I can write that is a column that has 4 components? Sure. So that's what this says. The direct product of bases for V1 and V2 is a basis for V1 cross V2. And that would even be true if we had different bases, the ones that aren't just 1, 0, and 0, 1. Like I could use chi plus x and chi minus x instead of z. And I'd still, by multiplying them together with the direct product rules, get a basis for the direct product space. But not all elements of the direct product space are direct products. So, for example, 1 over root 2 of up, down, minus down, up. How would I represent that as a column? What's 1 over root 2 up, down, minus down, up? As a 4-component column, what is that? It's 1 over root 2 times what 4-component column? 0, 1, minus 1, 0. 0, 1, minus 1, 0, because up, down is 0, 1, 0, 0. Down, up is 0, 0, 1, 0. So 1 over root 2 up, down, minus down, up is 1 over root 2, 0, 1, minus 1, 0. It turns out you cannot find anything. You cannot find two two-component vectors whose direct product is that. It turns out it's just not. So clearly I can add elements of the direct product space together to make things which turn out not to be themselves direct products. So the direct product space's dimensionality is the product of the dimensionalities of the two spaces that went in, right? So here it's each space has a dimension of 2, and the direct product space has a dimension of 2 times 2, or 4, and that always works out. But the direct product space is bigger than just all the direct products that you can get. And this probably shouldn't come as a surprise because, for example, consider R2 viewed as being the xy plane. So I'm talking about, in other words, the real numbers, R cross R, right? The real numbers, right? And then there is the z-axis is a copy of R1, the real number line. Well, R3 is in fact the direct product of R2 and R1. And certainly, if I take it's certainly true that not everything in R3, not every vector in R3 is a direct product of a vector in R2 and a vector in R1, and there's not enough time for me to expound upon that further, but you can convince yourself of that. I shouldn't have even said that probably. But in any case, the punchline here is that we've enlarged our space to handle situations where we have 2 particles instead of just 1, and we need 4-component column vectors if we've got 2 spin 1/2 particles to represent the result. And this statement right here, that not all elements of the direct product space are themselves direct products, is of profound importance because states which are themselves not direct products have a special name which you might have heard before, which are called entangled states. So if you've ever heard about entangled states in quantum computing and the Bell inequality and stuff like that, it's referring to what are called entangled states. This state right here is the wave function, the spinner, for a pair of electrons such that they have a total angular momentum of 0 and therefore also a z component of angular momentum of 0. This is what is called the singlet state of a pair of electrons. These 2 electrons have quote-unquote opposite spins, and it's what is known as an entangled state because there's no way to decompose this into a direct product, meaning there's no way to represent this as a state where there's some direction where both electrons have well-defined spins along that direction. It can't be done. Intrinsically, no matter what direction you pick, each electron is in a superposition of being spin up in that direction and spin down in that direction, and you can't disentangle it. You can't find any decomposition where there's another direction where both electrons are either spin up or spin down, or one is spin up and one is spin down along that direction. Intrinsically, for every direction, each electron is a mix of spin up and spin down. And entangled states are very important in quantum computing. Entangled states are important in the Bell inequality because the idea is if I have 2 electrons in the singlet state, they can separate for light years. And if I measure the spin of one of them and I get up, that collapses the wave function so that this piece goes away, and if I measure up for one of the electrons, the other electron has to be down if I measure its spin, even if they're light years apart. So Fred makes a pair of electrons in a singlet state, they fly away, and then Sally, 10 light years away from the original lab, and Mary Ann, also 10 light years away from the original lab, set things up so that as soon as the electron passes by Mary Ann, she measures it, let's say she gets spin up. She knows that whatever her name was over there, Sally, 20 light years away, is going to get spin down. Which is strange at first because it seems like I've made an effect travel instantaneously from here to 20 light years away. And so it seems like, and this is what Einstein thought would prove that quantum mechanics was invalid, because you could do something like that. So Einstein proposed that as a proof quantum mechanics can't be right, and we did the test with nature, and nature went to Einstein, basically, because no, this is right. But it doesn't violate relativity in the following fundamental way. You can't transmit useful information this way, because while Mary Ann will know what Sally's going to get for her measurement, Mary Ann can't be what Sally's going to get. Mary Ann can't tell Sally in time for Sally to be able to know herself before she makes the measurement what she's going to get.
The measurement is completely random.
It will seem like it. What you'll get is, if you do this multiple times, you'll get two sets of perfectly correlated random numbers, is what it comes down to. And so you can't transmit a signal this way. You can't transmit information like prepare, the Zorkonians just flew by with an invasion fleet. Because you can't control what you're going to get from your measurement. That's random, and you can't send a signal over to the other side to say, I got whatever from my measurement. To say the result of your measurement, you have to send a so-called classical signal, which can't go any faster than light. And so what you get is perfectly correlated random sequences of numbers. And so, in other words, you can only transmit gibberish this way. And apparently nature doesn't care about being able to instantly transmit gibberish, but it does care about being able to instantly transmit the Zorkonians are about to invade. Because if you could do that, it turns out then you could go back and kill your grandfather and all that kind of stuff. And so, before you were born, all that kind of stuff. So anyway, the end. Yes?
What you were saying is that if this guy, the person over here, take a measurement, then you could have the wave function already.
The point is
this
that,
person over here take a measurement.
well, the point is that when the two particles are entangled like this, they are in a single quantum state. So a measurement on either one of the particles performs the collapse of the wave function into either one of these. So as soon as you do a measurement, which if I measure the first particle get spin up, I'm at this point, right? So as soon as I know my particle spin up, I also know the other particle is spin down. So if she measures, she's got to get spin down. She is guaranteed to get spin down. She doesn't know she's going to get that, but Mary Ann knows she's going to get spin down when she makes the measurement. Unfortunately, Mary Ann can't tell Sally that she's going to get spin down before she makes the measurement. She knows she's going to get, Mary Ann knows Sally's going to get spin down, but she's not able to tell her that beforehand.
So why don't we get to set a random number?
Well, I'm saying if you did this for many, many particles, every measurement is random. So half the time you get spin up, half the time you get spin down. So you'll just get a random sequence. And the point is that you'll get two random sequences which are perfectly anti-correlated. Everywhere there's a 1 over here, there's a 0 over there, so to speak, right? Yeah. But they're just random sequences. What's that?
Good evening.
Yeah, right. Each one will be 50-50, and they'll be perfectly anti-correlated. Every time that one's up, that one's down, and vice versa. But there's no useful information there, because she can't decide, I want to get spin up when I make the measurement. If she could decide, I want to get spin up when I get the measurement, then she could transmit a signal, because if I could choose 110011, I'd be making a binary code that then would be being transmitted to the other person 20 light years away. But since I can't force any particular result of the measurement, all I can generate is a random sequence, and all she'll get then is a random sequence that's perfectly correlated with mine but doesn't contain any useful information. And it turns out nature's okay with that. Nature doesn't want you to send signals faster than light, but nature's perfectly okay with sending gibberish faster than light, interestingly enough.
Okay, thank you.
Yeah, remember that picture I remember.
Yes.
Uh-huh.
Yep. Uh-huh.
Ah, yeah.
Yes, exactly so.
It's not totally